people are becoming more, as people are becoming more and more aware, we are on quite an alarming trajectory, with us heading towards possibly towards 3 degrees by 2050 if we don't change what we're doing. We're currently at 1.2. Sorry, I'm struggling with my slides aren't moving. Sorry, my
they're not moving on.
Oh, yeah,
moving on now.
It's a delay.
There we go.
Yeah.
Okay, it might be because I'd had to click the record, just to turn the recording thing off my screen. So the first thing that I thought about was, what can I do? And a few weeks later, I went to EcoBuild, which is now called Future Build, and I came across a retrofit coordinator course. I also decided to educate myself a bit more about this situation and read Naomi Klein's This Changes Everything. And I joined some local campaigning groups, and we did an event in the November of 2015. And I very much felt like this. I felt like standing on a soapbox, but I didn't quite have the courage at the time. And I certainly didn't imagine that we would all be talking about it, that everyone really would be talking about it by this year. In 2015, it seemed a topic that was hard to bring up. And through my campaigning, I came across Project Drawdown, which has 100 ways that you can reverse global warming. And they have a lot of different solutions that are associated with the building industry. And this is the ones that they've collected. These are the ones they've collected. So it turns out that I could do quite a lot. And now I want to think about how much our buildings emit. Across the global sector, this is our global CO2 emissions by sector. It's 28% on heating buildings and lighting them, and then 11% on construction. But the construction kind of grows a little because the concrete and steel industry account for 23% of global emissions, and industry a further 20%. And much of this is connected to our buildings as well. So, you know, in thinking about that, how much are we going to be building in, say, the next 40 years, the next very crucial 40 years? So if you think of the number of buildings in New York, this is how much we're supposed to be building within 1 month. So that's, this is a year, this is 10 years, and this is 40 years, 480 cities of New York, which is the entire building stock of the world built all over again. So obviously, it's quite a big problem in that buildings emit such a huge, you know, the building industry accounts for such a large sector of carbon emissions. But we also have an opportunity. And that is when you look at materials. So if you look at conventional materials versus carbon storing materials, which are materials that have grown and stored carbon in their growth, and then that makes quite a big difference. And this graph shows how, if you the general if we starting at 0, conventional materials are starting at that point and creating a whole load of carbon, and over 60 years it's quite a bit of carbon. And then if you take into account that it's a grown material, you can take that starting point to well below that 0 line. And then the theory is that although you might be using the same amount of carbon to harvest, manufacture and get it to site, you are below the line, and therefore it can be seen as a carbon storing material, it's carbon storing building or addition to buildings. So overall, between now and 2050, both operational carbon and embodied carbon in the end up being about the same amount. So they're equally important. And the building that I'm about to talk about could have been done in different ways. And say you had a new build, if you've got high carbon materials, they can be hugely emitting. You can improve the materials a bit and reduce the emissions. I think with us, we got to about the yellow, and I'm sort of trying to take my practice all the way to the green eventually. So we can pivot the way we live and work so that it's not just an existential threat, but we are part of the solution. And retrofit is important because, yeah, it's part of the solution and provides comfort, improved health, raises awareness, and potentially influences others. And I very much believe that it's important to tackle this on every single project. And then there's the issue of our old building stock, which is leaking heat quite dramatically. And these are some of the average heat losses across the different parts of the building. So we're leaking heat and we're also quite cold. And at the same time, we've got an energy crisis. This was a funny slide that I came across. Well, not funny, you could say it's sort of tragic and funny at the same time, but some suggestions for saving money, which in the context of the previous slides seem almost, quite sad in a way. Sorry, I can hear somebody talking, sorry. I don't know.
Excuse me, could everyone mute, please? Someone, we're hearing a conversation coming in.
So wouldn't it be better to, instead of attempting very small savings, isn't it better to do something like this, where we wrap the whole house in a woolly blanket effectively? And the building here on the left has been retrofitted and the one on the right hasn't, and you can see the amount of heat loss coming out of the one on the right through this thermal camera. And just to give you a quick understanding, our homes use 35% of all the energy used in the UK and emit 20% of carbon dioxide emissions. So now on to the project. This is what we started with. And this is a bit of the inside once it had been stripped out, and the basement. And just to recap what retrofitting is, it's tackling the insulation, ventilation and heating systems. And today I'm going to talk in principle about the insulation and not really touch on ventilation or heating systems. Things that trigger retrofit are all listed here. In this project, we had 2 extensions, a lot of essential repairs, and it was a new home. And it's a solid wall property, which is harder to treat than, for example, cavity wall buildings. And we started with the lowest possible energy efficiency and a score of 1, or rating of G, and a heat demand of 600 150 kilowatt hours per meter square per year. And I didn't know what it really meant, so I'm going to explain to you as well. So if you look at the typical leaky house, the average is about 300 kilowatt hours per meter square per year. Modern house reaches 150, and the ultimate energy efficient house, a passive house, gets as low as 15. So we've started with 650. And then we used a passive house planning package to look at the measures we were putting in order to work out what the heat, how much we needed to heat it once we'd put those measures in. So a typical 220 thick historical solid brick wall has a U value of about 2, and single glazed sash windows can range from 5 to 7. I'll just keep these figures in mind as I tell you where we took ours to. So we got the brick walls to between 0.3 and 0.32. So we started with a 2 and we got to 0.3 to 0.32. The windows, starting from a 5 to 7, we got down to 0.85 to 1. And the rear walls, the roof and the basement and the extension all at 0.15, which are all passive house levels. And to do that, we used natural materials, and the insulation in principle was wood, fibre and cork. Yes, and sorry, just go back there, and the insulating lime cork, lime and cork plaster called diathanite. So this is what we started with. This is once we'd taken the ground floor out. You can see the ground floor line, the blue line there. And the contractor bought a lot of the materials up front, which are stored there on the site because of the huge fluctuations we've had in prices. And also you can see that they're sort of starting to store the bricks that they managed to salvage from the building. And we took the building quite significantly apart. Much of the roof came off to have the 2 dormer extensions on the top floor. The back wall was in really, really poor condition, so we also took that down, which was quite a big move, really. And there you can see the back wall was starting to build that up again. It was all in timber construction. And this is again the back wall, and you can see wool. We've got some wool there, and the wool insulation there, and the bricks that had been salvaged from when they took the back wall down. Wool insulation is interchangeable with flexible wood fibre, and because the wood fibre was low in stock, we supplemented it with wool as well. So this starts to show you how we then filled the timber frame on the rear of the building back up with flexible wood fibre and then solid panels of wood fibre on top. And the full depth of insulation was 280 millimetres. So 140 was within the timber structure and another 140 on top. And that gave us our new value of 0.15. And on the left here, you can see the steel structure buried inside the insulation, because it's really important to try and get as much of the structural elements with insulation on the outside if you possibly can. So this, on the left, it then got covered up with the solid board of insulation. This just starts to show you the different layers around the windows, and the white stuff here is called compact foam, and it's it's not a natural insulation, but it acts like wood, and it gives you the ability to fit windows within the insulation zone, because you can screw the windows into it. And this shows the build up of the back wall that I just described, and then we hung bricks off the back and there's a 50 mil ventilation zone. And here we also insulated the floors with the flexible wood fibre. This is before they've really put they put sort of small bits all along the edges to stop any gaps, because the sound will pass through gaps as heat will. It's really important to have no gaps. This just shows the dormers on the top floor, and the blue tape here on the top of the OSB, which is the sort of the orientated strand board, which is the timber board that you can see there with the blue tape. That's to give us an air tightness layer, and every single screw and nail fixing through that board has got a piece of air tightness tape to stop air leaking. Because once you've insulated the walls, it's really important to make sure you don't get heat loss through air loss. And here they've also put a little bit of extra, they've painted over a bit more air tightness on top of the board. And then we lined the whole thing with something called wood wool, which was then able to carry our lime plaster on the inside. This is a nice shot of our client seeing the view through the windows for the first time and exclaiming, "Wow," which was very satisfying at the time. Just a quick thing on cold bridges, because I don't have a huge amount of time to talk through everything, but cold bridges are where you've got a piece of structure which has passed through the insulation layer, and you have to be really careful with these because you can end up with the cold passing along that piece of structure and then attracting moisture to it, because it's a bit like if you take a cold glass out of the freezer and bring it into warm, moist air, all the condensation forms on it. So you don't want to have a cold element coming into the warm building. And we used a material called aerogel in hard to treat areas like this. It's very expensive, so we have to keep it to a minimum. Our strategy for the main walls, the external walls of the house, and this is also the party wall here, was to use a material called diathanite as the base layer to smooth out, to give a smooth surface, because underneath it was just the brickwork, exposed brickwork, to give a smooth surface to put the insulation layer on top. We use diathanite because it itself is insulating, so it enabled us to have better U values on those walls. Just a tiny bit on the extension, we used a block called porotherm, which is a hollow brick. It's very quick construction. They're trying to decarbonize it, but it is a fired, bricks are fired. However, it acts as, which has a carbon impact. However, it works both structurally and because there's a lot of air in it, there's less brick, and it's also an insulating material. On the slabs in the extension and at mid-level, we were able to use this product called Glaypor, which is recycled glass. And that you can get it in slab form and in this sort of coal-like pieces, and it was very it's very good at dealing with moisture, and you can use it below ground. And a lot of the natural materials, obviously the grown materials, if you put them below ground, there's a risk of rotting, so tend not to use those once you get into the below ground areas. And now onto the basement, which is all below ground. Basements are the most difficult thing to do in a low carbon way. We did what we could, but I wouldn't say we were 100% successful, but I'll tell you what we attempted, and you can make up your own mind. You can see on the right there, those white panels of insulation. This is polystyrene based one called EPS. It's not as bad as PIR in terms of its carbon impact, and it can go below ground. So we use that to line the underside of the underpins, and I used something called a Ubicus calculator, which allowed me to look at the build-ups. I won't dwell on this because there isn't a huge amount of time, but this started to show me how we might build up from the earth. There's the polystyrene, then the reinforced concrete, then an egg crate material to capture any water coming through, and then we were able to put a cork and lime render on the inside. And you can see down here it gives me the U value, and the fact that it's nice and dry and its contribution to the greenhouse effect. If this starts to this calculator helps me to find out if there's going to be water in the construction, and it starts to show it up like this. And once it does that, I either look into further investigations through something called a woofy calc, which we used on the basement to make sure we didn't have any problems with moisture. One of the things I attempted to do to remove the steel from the project, because steel and concrete are the highest carbon materials, as well as aluminium. And I looked at using something called basalt bar, and it looked really great in theory. However, in practice, and it also had the same price point as steel reinforcement bars. But when you pour a basement, you need to connect it to the underpins. The slab has to be connected to the underpins, and you need curved bars at the edges and along the connections. And the curved bars turned out were £48 each. And so we had to drop this as an idea. So we went back to using steel reinforcement bars. I haven't given up on basalt yet, though. It's something that I will continue to look at as a potential for replacement. So here you can see the reinforcement going in the basement. And the other thing we did was we used we got a very bespoke concrete mix, which was just check the time, sorry. I'm running out of time. Try and whiz through. The concrete mix had an insulation, something called Litag. It was made more lightweight, and we poured it in U sections to try and get the largest pour possible. This is because it was a bespoke mix. We were the only site using it, and they had to provide us a minimum of 2 cubic meters at a time, and we couldn't always pour that much, which meant, tragically, my theory of a really low carbon concrete that was also insulating was, in practice, we had to throw some of it away. We then used the cork on the inside, which was on top of the recycled sea plastic, which was what was stopping the moisture getting through to the cork for any water that sort of pushed through the reinforced concrete. So of the high carbon materials that we used 63 cubic meters of low carbon insulating concrete, with an apparent effect of a 71% saving on carbon emissions, although the structural engineer isn't fully convinced on that. And we had to discard 23 cubic meters of it, but we did manage to salvage 14 by using it in the extension foundations instead of the blocks that we had specified there. We also used 40 to 50% less steel than projects of this nature on all the structural elements of the roofs in the extension and the top floor. And that had an estimated saving of about £15,000. And we used quite a lot of wood fibre, cork sheets, structural timber, OSB and wood wool. I won't go into it in any more detail than that because I want to give Jeremy, who's up next, enough time for his talk. So we started with a heat demand of 650 kilowatts per metre square per year. And we have a predicted heat demand of 30 to 35. Not quite passive house levels, but getting pretty close. Passive house levels being at 15. That's a 95% improvement. So this is what we started with. This is how it will look. It's all starting to come together inside. You can see in cream there, that's the lime plaster, and the pinky plaster is gypsum plaster on the internal walls. This is all the lime plaster on the top floor. These are my collaborators. Johanna Arbo Jackson invited me to join the project as the retrofit coordinator, and Paul, Thomas and Trix were all involved at different points of the project. And these are the key team members on the job. So I might be doing a little bit of this after all. This is the talk I did in March. And that's it from me. Thank you very much.
Thank you very much. I'll do a round of applause here. Thank you, Natalie. 95% improvement. That is,
yeah.
You know, it's a shame it isn't passive house, but rules are rules.
Yes.
Is that right? Yes. Well, thank you ever so much. That's smashing. Actually, there was just one, probably just a couple of quick questions, or some were from me, so maybe we could take those. Someone's asked, how do you know if you've got a cavity wall? Now, I think I know the answer, but you'll have a more accurate way to explain.
Okay, so the easiest way to tell that it's a solid wall is you tend to have a mix of bricks going in different directions. So you get a stretcher, which is the long edge of the brick, against a header, where you see the short edge of the brick, because the wall needs both of those to work well structurally. And when you have a cavity wall, the bricks are all stretchers. They're all the long side of the brick.
Yeah, thank you. And I was just asking, U values, is it the lower the better with the U value?
Yeah.
Yeah, lovely. And what is aerogel made of?
I think it's silica, something,
right,
material. I'm not really sure.
Yeah.
I don't want to answer that because I'm not 100% sure.
You're not the manufacturer,
it
fair
also
enough.
has a name called space therm, so I think it was used in outer space, in the rockets. I think it might have been used in that.
Okay, thank you very much. Well, thank you, Natalie, and we'll come back to you at the end, if we may, with other questions. Sure. And now I'll invite Jeremy to share his screen. Sorry, I'll introduce Jeremy Stacey of Jeremy Stacey Architects. Please, could you start your presentation?
Well, thank you. Natalie, that was really terrific, and puts my talk to shame. I've got no figures, and I love concrete, but you can recycle concrete. But anyway, that was really brilliant. Thank you very much. Well, I've been in practice with my wife, Rona Fleming, in Norfolk for the last 30 years. And I thought it might be worth explaining a bit how we became interested in reducing energy consumption from buildings. In 1997, we were very fortunate to be chosen to, let me put an image up. Am I sharing my screen all right, Mary?
You're not shared yet.
It takes a little minute to pop up, Jeremy. Have you clicked share screen?
I clicked shared screen.
Right. Let's just give it a minute, because you're over in Norfolk, aren't you?
Yes.
Have you also clicked
No trouble.
confirm? And there you go. There you
Are
go.
you sharing?
Yeah, yeah, it's coming up
Okay.
now.
Yes. Can you see your notes on the screen, Jeremy?
No, I just talk.
Yeah, but what do you see on your screen at the moment?
I can see a picture of the building.
No, you've shared the wrong screen, I think.
Oh, let me move this over. Here you go.
That's the one.
Ah, yes.
No, so is that better?
Yeah, can you make it bigger and to fill the whole screen?
Righto. You see, unlike Natalie, I'm not used to this.
Or just as big as POS, yeah. But yeah, that's visible.
Does that look really small? Is that better?
I think that's okay. Yeah, I think we'll run
it'll
with that.
Be okay for photographs. I
Yeah,
think, yeah.
thank you. Yeah.
Right. I'll try and make it bigger. Anyway, let's go back to say how I became involved. The it's gone.
Right. Do you want to try?
Can I suggest that you unshare and just try sharing it again, and then it should give you a whole load of options, and you should be able to share just the one that is your presentation, because what we're seeing is your whole screen.
Is that better?
That's better.
Yeah.
Better-ish now.
Yeah, thanks, Natalie.
Okay.
See how you go.
Right. Right. So anyway, we became interested in low energy buildings.
Lost it again.
Try the next one, Jeremy. It's a matter of interest.
Okay.
I don't know why it's doing that. It's odd. It was all right when
we're on
tried
the
earlier.
end of the telephone line in Norfolk. Well, let's try just explain. Can you see that?
Yes,
Yes,
that's
you're on to
clear.
your second slide now. Yeah.
Yeah, good. Now, we were asked in 1997 to design a new urban block in Kings Lynn, and we wanted to do it from a low energy standpoint. And on this project, we were greatly helped by a young mechanical services engineer called Hannah Blossom from Fulcrum Consulting. And this building, if I go to the next slide, this is a section through the building. And what we wanted to do is it's a cavity wall, but we wanted to have 200 millimeters of insulation in the cavity, 300 millimeters on the roof, and 100 on the floor. But we also didn't want to have air conditioning, and we didn't want to have a conventional heating system. So, and Natalie can criticize me after the talk, but we opted for hollow core concrete planks for the floor. And we used a system called Thermodeck. And this is a proprietary system where they link the hollow cores together. And it's a bit like the Romans did with their underfloor heating, with air going underfloor. Because when you link the cores and the hollow core planks, the planks are a meter wide and go right across the building. And there are 4 cores in each plank. When you link the cores, it's a rather raggedy link. They kind of bash it open. And because of the raggedy link, air passing through the cores gives off more heat. So the way the building was heated and cooled was quite simple. During the day, imagine the building is cool in the morning. So in the day, all the heating and ventilating air, and we have 100% fresh air, all that goes through the hollow cores of the planks. And so gradually, the planks absorb the heat from the people in there. So it's by the end of the day, it might be warm, but no air conditioning is needed because of the mass. And I'm very interested in thermal mass. So no air conditioning is needed. And then, but at the end of the day, the building's hot. So what happens next is that at nighttime, cold nighttime air purges the hollow cores of the floor planks. And so by the time people come into the building the next day, let me show you another, here's the building. By the time people come in on the next day, the building's cool. So we're using the thermal mass of the hollow core long span concrete planks. I think the span was over 13 meters. We're using these hollow cores to moderate the temperatures inside the building. And the other nice thing about this is that there are no suspended ceilings. So if you love concrete, and I was brought up as a student in the early 70s, really enjoying the work of Le Corbusier, and I went to stay in his flats and in his monastery and so on. But this building, when you go in, you look up and you see the exposed face of the concrete plank, rather than a suspended ceiling with air handling ducts inside. So all the air handling ducts were down the middle. You can see on the drawing here are the air handling ducts down the middle. All the lighting was from the edge on lighting shelves. So in a way, it produces a really rather lovely, cool, calm environment. And we were quite pleased with that. And that was 20 years ago. And I still enjoy the use of thermal mass to moderate internal temperatures. Now, if I go on to the next image, here we have, and this is a project we did probably 10, 12 years ago, but it was a cottage and an extension. Now, the cottage we did in completely green. This was really a lesson to us and the client. We did the cottage in, we used hemp insulation in the roof and hemp on the walls. Incidentally, initially, the cottage was covered with cement render. And one thing about brickwork in cement mortar or cement render is it doesn't breathe. And as soon as you get a crack in it, water gets in and it can't get out because the cement render doesn't breathe. And then in the winter, the water freezes and then it blows. So on the cottage, we did insulated with hemp between the original timbers. All the original timbers were restored. Lime render on the outside, lime plaster on the inside. And then on the floor, we used the glass insulation pellets, a limecrete floor, and recycled Norfolk clay Pamet quarry tiles. So that's the cottage. But next door, still holding on to my love of thermal mass, next door the building is in concrete blocks with an EPS insulation and a thin coat render on the outside. In places it's covered with timber to represent what was happening in the building. Now, once the projects were finished, some very interesting things were noted. And these were just things which you could feel. The cottage, the air quality in the cottage was much better than the air quality in the other building, in the extension. But the cottage needed a lot more heating because we could only insulate with the hemp within the thickness of 100mm original studwork walls. So at the end of the day, because it was an elderly couple living there, we wanted to keep steady state temperatures in the extension. And by having underfloor heating under stone floor, the heavyweight internal blockwork, the insulation on the outside, in effect, the building kind of ended up like a huge night storage heater. And it was very easy to keep steady state temperatures. But it needed more ventilation because cement products and brickwork in cement and a lot of modern insulation materials don't breathe. So this was an interesting exercise and a lesson to ourselves. And I'd still perhaps go for, if the building is occupied for a long time by people not moving about much, I still quite enjoy the heavyweight construction. But at this time, it didn't have heat recovery ventilation, but it should have in the future. So moving on to number 9, Alexandra Park Road, which is a very nice little 2-story, a garage. There's a garage basement and there's attic rooms. Here's another view from the south. And our clients really loved the house, and they liked all the quirky aspects of it, and they didn't really want to change it much, but they did want to reduce their carbon emissions from living in the house. So we then, this is the back. So when you see the flank wall, the wall on the side, that kind of cries out to be insulated on the outside, as does all this brickwork here. The reason for insulating on the outside was that the clients, who are a lovely couple, Nadia and Zachary, who were very, very keen on reducing the carbon emissions from living in their house. And it's to their credit that the project continued in the way it did. Because generally speaking, most of our work is for publicly funded work, arts organisations generally, or organisations providing art therapy and such for young people. So we tend not to do much private work. And on our other projects, we're not allowed to go over cost. And so like all the time on this project, I kept telling the client, you know, if you want to do this, it's going to cost more, but they were very keen to do it. So looking back here on our next image. So inside the house, there were lovely details which the client wanted to keep. And I spoke to Natalie earlier yesterday, and we both agreed that as architects, we need to look after our clients, and we try to ensure the things they want to do can be achieved. And on this project, one of the things Nadia and Zachary really liked was the quirky details inside the building. Here's some timber details, which are unusual, and they wanted to keep them. So here we have this curious beam in timber, interesting skirtings and so on. Here's another picture of this. So this is the flank wall, which I thought I'd really love to insulate. And so if we did it on the inside, you would lose a lot of this. So we insulated in the end on the outside. And you wouldn't believe the panic the planners threw into. The conservation officer wouldn't discuss it with us. Initially, when we put in for planning, the planning officer wanted to refuse it, which I thought was quite extraordinary. Sorry, I'll just pop back to the house. And of course, when here's the house. So the planning officer was completely she could not communicate with us. So we had to be extremely polite and do a great deal of work to demonstrate that this was all a good thing. And in the end, we our client contacted their local councillor, and we managed somehow to send information direct to the sustainability officer, who actually thought it was all rather good. But the planning officer couldn't cope with putting insulation and a render on this brickwork, even though if you look right across the street, there's rendered houses, and the front of this house was also rendered, and next door there are rendered buildings. So we had to go around the area photographing buildings with render on. And eventually, of course, if you produce enough information, you get it through. So if I go back to thermal mass now, this is where I live. And 32 years ago, Rona and I moved into this farmyard and lived in a caravan for 2 years while we converted a small farm building into our temporary home. And then gradually, 30 years later, this is our final completion. But again, talking about thermal mass, this is a tiled floor, and we have massive south-facing windows. And if you face south, you get fabulous amounts of solar gain. And you just got to watch it when it gets too hot by providing easy forms of ventilation. And generally speaking, because hot air is displaced by cold air, if you have a big opening at the top, you'll ventilate the building. So we found, and and Natalie, you'll be horrified again here by concrete block walls, but you can get recycled concrete block. At the time we did this, it wasn't. But we have two large concrete block walls in the house. These face south and they warm up fantastically. So at the end of the day, they become like, here's another fair face concrete block wall. They become like big night storage heaters. So I was looking forward to doing the questions to hear Natalie's response to this, because I'm quite, as you can probably imagine, I'm quite passionate about thermal mass and the use of heavyweight materials to keep that. So throughout the last 2 months, since it started getting cold, when the heat wave went, we've never needed any heating. When it's been 14 degrees outside, it's been 21 or 22 degrees inside. And that's purely through thermal mass, through the fact that all our areas of heavyweight materials have heated up. And even at night time, the temperature doesn't go down. Having said that, it's glazed on one side. On the other 3 sides, there's 175 millimeters of insulation. So it is well insulated, and there's 400 millimeters of insulation in the roof. So going back to Nadia and Zachary's house, so on the plan, very interesting idea the client had. They wanted to open up all the ground floor, which is really good for ventilation. They decided not to have the sliding partition doors in the middle. So all the ground floor is opened up. This wall is gone here. So you come in, you can see right through. Now that caused a problem with means of escape from the upper floors. So we had to install a water mist system, but just on the ground floor only. And that means that all the ground floor areas are as one. This is the flank wall I mentioned, and you can see on the side there's quite interesting detail. So this was insulated with 200 millimeters of EPS with a thin coat modern render on the outside. And this is the same insulation thickness as we were doing in 97. And I think I still keep to that view that really you just need lots of insulation. And if you can benefit from the thermal mass, that's a very good idea, because this side wall here will absorb the heat from inside the rooms. And the heat, when the temperature, because of the way heat works, the temperature always goes from a high energy to a low energy. So the heat will come from the walls into the rooms. And because all this is open plan, the heat will rise up. One thing the clients didn't want, I wanted to put a fan on top of the staircase in the at roof level to send the heat back down again. They weren't happy with that. But when we lived in our temporary accommodation next to the barn I've shown you, all we had was a wood burner, but we had a fan in the ceiling, and that brought the temperatures about 4 degrees higher once the fan was on. So my time, I've got 5 minutes, so I'll just run through the other. That's my house. I'll just run through here. That's the ground floor plan, and then this is the first floor plan. So again, keeping insulation on the outside, and here's the second floor plan, insulation on the outside. Now, if I go back to the first, where we had decorative details on the outside of the building, we put 200 millimeters of insulation on the inside, but only up to windowsill level. But as you can see from this drawing, the windows are quite big. So I wasn't too worried about that, because we would be getting valuable solar gain from the windows facing south. This is a detail of how we did the insulation on at the south facing windows by building a stud wall and packing it full of insulation. Here's a section through the building. As you can see, this is all open, so it would be good to have a fan up here, because we had underfloor heating in between the floor joists, and the fan would send that heat back down again. And looking at the roof details, we had 2 areas of roof. We had the dormers on the flat roof at the back. We had someone help. So I work with a very nice chap called Colin Williams. He used to be a bricklayer, Then he became a building inspector, and then he did a PhD on clay lump buildings. So he's an expert on clay lump, but I've yet to find a client who wants to build a clay lump building, because with clay lump, you dig it out of the ground on the site, so there's no transport at all, and then you build it. And Colin, as I say, he did a PhD on the subject, and if anyone is interested in doing a clay lump extension, I'm sure he'd be interested. But at roof level, we put 100 mil of insulation between the rafters, 75 under the rafters, and likewise on the flat roofs, 130 above the flat roof and 100 below. So we had 230 there. And when dealing with different thicknesses of insulation, you need to put the thinner insulation underneath the thicker insulation. Otherwise, there's a risk of interstitial condensation, which would occur at the junction between the two layers of insulation. Now, Natalie mentioned thermal bridges. It's very important to avoid thermal bridges, which is where you have the risk of a cold part of construction facing the external air coming to the inside. So as we are placing 200 millimeters of insulation on the outside of the building, we needed to extend the roof 200 millimeters to cover that and insulate the top. Likewise, at the back of the building, where there are some lower pitch roofs, we ensured that we reduced cold bridges by extending the roof and adding more insulation. Now, onto the windows. Now, this shows the existing and proposed windows. So existing, proposed, existing. Now, you wouldn't think the planners would get so worried about that, but I drew every window out, showing how the proposed triple glazed, argon-filled triple glazed units in firmly broken timber and aluminium frames would look almost the same. Not quite the same as the old windows, but the old windows were pretty horrid anyway and way past their life. So we drew all the windows out to try and persuade the planners that they'll be okay. And then here we drew the window sections out. Here's at the front. Now, eventually, this is to show how, we're not really changing it. Here's at the front, we kept to timber because the client was particularly fond of the front windows and they were part of the kind of charm of this house. But we originally put in for triple glazed. In the end, we decided to use double glazed, and we used on the front windows insulating glass. So it has it's double glazed with one thick layer of glass, I think it's 12 or 15 mil, and one thin layer of glass. And the overall thickness of the glass panel was such that we didn't have very heavy timber frames. So it looked, in effect, the same as before. Now talking about heating, I love to draw sun path diagrams on buildings, showing where the sun rises and sets. And this then encouraged us to have photovoltaics. So here's the roof plan. And so at the front of the house, there's 6 photovoltaic panels. Again, the planners got pretty upset about that. And our dear clients went around the area photographing where there are lots of photovoltaic panels on the front of buildings in the conservation area. So we had all this backup, but even then, they said they would refuse it. They didn't in the end, of course. But at the back, there are 4 panels. And I don't, in the summer months, Nadia and Zachary haven't needed any electricity. But the reason why I was particularly keen on photovoltaics was that the building would be heated with a heat pump. And I spent a long time at the beginning of the project advising the client, because I was very worried about their heating bills, because at that time electricity was 3 or 4 times the cost per kilowatt hour to heat than gas. The client was very keen to avoid gas because of carbon emissions, and also keen to avoid all the poison and stuff going from out of flue gases. So even though we wrote a lot about improving the air environment of the area, it didn't, until the very end, it didn't cut much mustard with the planet. This is just showing how the photovoltaic panels were recessed into the roof. Another issue, because we were increasing the insulation, we needed to raise the roof level by 28 millimeters, which again was one of the areas the planners were concerned about. Now, we had a meeting with the local councillor, and 28 millimeters, frankly, a roof of a Victorian house would be out by 28 millimeters from one side to the other. But we had to do that in order that any water coming through the tiles could drain off. So we recessed the panels on the front elevation, and it looks pretty fine. So there's the project completed. So here we have the insulation on the outside, and coming up, so I hope I won't overrun. Here's the solar panels on the front, and here's the front elevation, and it's just as it was before. You might notice that perhaps an extra hinge on these windows, but in terms of planning terms, it really was a fuss about nothing. And I think this comes back to people not wanting change, and especially not wanting change when the outcome is something really good, because the outcome of this was that the building was well insulated with 200 millimeters of EPS insulation on most of the external brickwork. On the inside, up to windowsill level, it was insulated on the inside. Windows at the rear were triple glazed, aluminium, firmly broken windows with timber frames inside. On the outside, we used a thicker glass, which had the same value, U value, as the triple glazed windows at the rear. So, Mary, I've overrun. I better stop.
That was splendid. Thank you very much. I'm returning. Thank you, Jeremy. You reminded me with your thermal mass of my friend's grandmother's house in Ireland, because that was traditionally how you kept a cottage warm. There were great big thick walls. So, yeah. For thermal mass, that's great. Thank you.
Can I ask a question to Natalie?
Certainly, yes. I was thinking you two might like to have a bit of a dialogue. That'd be very interesting if you can listen in.
Natalie, from the very beginning, I showed how I was keen on thermal mass, especially using hollow core planks to moderate internal temperatures in an office building and avoiding air conditioning and heating. In fact, there's only a tiny boiler on very cold days, but also creating wide-span structures and a nicer internal environment without suspended ceilings. Having seen my presentation, am I a dinosaur? I'm a dinosaur, am I?
You need to unmute, Natalie.
I think that's a funny question, but you know, there's still a lot of interest in the use of concrete. My way to try and maintain thermal mass and but avoid concrete is to do what you suggested yourself, which is to try and use the soil. This my next project. One of my next projects, I want to try and use the on-site clay and mix it with waste. It's something that there's a company called HG Matthews are offering, and they've done it on some big commercial sites where they take the waste rubble and clay used that's coming out of the ground from the foundations, and then you can get it over to them, and they will mix it and turn it back into unfired blocks, called Strox. And this is something I want to explore with one of my future projects, because it's a great way of having the thermal mass, but not having, but keeping it very low carbon. And the other thing I have, it's a question I want to put to them, to HG Matthews, is could we potentially, but I haven't totally investigated, it's just something I'm thinking about, but we use this product called Lytag in the concrete mix in Muswell Hill, which made it an insulating concrete. And I'm wondering whether we could make the blocks also insulate, a little bit insulating, by adding Lytag to the mix. So that's something I'm interested in exploring.
I think another aspect of this whole argument is to reuse buildings. I think that's something which needs to be stressed, because lots of architects have big egos. I mean, I have a very small ego, frankly, and I'm not interested in doing big fancy buildings. And I think since our building in King's Lynn, which I'm still, although it's a quarter of a century ago, I'm still quite proud of it. We've done a great deal of our work on existing buildings. And then one, especially if they were built before about 1850, you're given a whole palette of lime-based materials, lime plaster, lime mortar in the brickwork. And so it's very nice to then be able to use hemp, or we've used wood wool slabs and then lime rendered over on the outside of buildings. And because the whole setup is breathable, you have a much better internal environment and reducing the carbon emissions during construction. So I think architects need to be encouraged to look at old buildings as a source rather than something to knock down and rebuild.
Absolutely. I think all the techniques that are being put forward by the sort of companies that are in this area are all referring back to old techniques. It's all like going back to 100 years ago. We did it. We built differently then, and it was a much lower way, it was a low carbon way of building. And so a lot of those techniques are being revisited, but also from a modern, with a modern take on it.
I think often the problem with old buildings is that they're damp, and people have put strong cement renders on to try and cure the dampness, either inside. When I worked in London in the early 1980s, I worked with a firm who did a lot of housing association work. And the first thing they did was inject a damp-proof course and put cement render on the inside. Whereas in fact, that's the last thing you should do on a Victorian building. You should repair the lime plaster on the inside, and where you can, reduce the ground level on the outside, so you get less rising damp. And once you've repaired all the lime, the building will breathe naturally. And we've recently done work with Great Yarmouth Preservation Trust, and we never ever put in damp-proof courses. A building to start with, if it's been very wet, may take 2 years to dry out. But we never also used wood preservatives, because for dry rot, we never put chemicals on because they're harmful to insects and so on. And when we have beetle attack, we always put in our specifications that the contractor should introduce families of spiders, because spiders eat the wood-boring insects. So that's part of our standard specs. But I think a lot of harm has been done to old buildings by trying to make them watertight by using materials which are just not part of the language to which the buildings were built.
Absolutely. And when I studied retrofitting, they talked about doing, I at the Retrofit Academy, the course was put together based on 150, 100 case studies, where they've been each case study had been given £150,000 to spend and experiment. And a lot of the experimentation worked out really badly because they put vapor closed materials on top of old buildings, which is all vapor open. They'd assimilated all that information and come to the conclusion, very much that you have, that you need to keep it all vapor open, and the building physics of the old building needs to be maintained, and then the building works really well, and you reduce the risk of the effect of the cement on old brickwork, for example.
It destroys the bricks in the end because the cement is so much harder than the brick.
Yeah,
That's why sorry.
Yes, I've seen a lot of bricks falling on especially chimneys that have been repointed, or the edges of buildings where it gets the most moisture, where the bricks just start blowing as a result of the cement pointing.
Repointing a lime mortared brick wall in cement is criminal because, as Natalie said, the cement being stronger in weather conditions, the bricks fail along the line of the cement. So you see this strong cement, new cement pointing, standing proud of the bricks, and it'll be the last thing standing when the whole thing collapses. The cement won't go away.
Thank you. Can I interject with a few questions from the audience?
Yep.
Tony Edwards asks either of you, what value is British Standard PAS 2030-35 dated 2017 energy retrofit for old homes with public funding for all old buildings? This was set up in 2015 by a government committee to avoid defective building works. On that side of you.
Yeah, so I studied with the people who put PAS 2035 and probably PAS 2030 together. So I think the PAS 2030 is more for the builders, and I'm not 100% on this, but the PAS 2035 is for retrofit coordinators, which came out in 2020. And it is a standard. They're trying to elevate the industry to be able to do the retrofitting well. We don't. There aren't many contractors who know how to insulate buildings properly, to make sure that there's no cold bridges, to deal with air tightness. There is a really big skills shortage, and the Retrofit Academy, who were involved in putting, and Peter Rickaby, who's part of one of the authors of PAS 2035 and one of the key teachers, have put it together to basically ensure better standards. And I think with publicly funded buildings, you have to have a retrofit coordinator, and you have to get to get any funding on bigger buildings, not sort of small domestic buildings, but say housing association sets of buildings and things like that. You need to be PAS 2035 compliant to be able to get the funding. And it's just quite rightly a standard to make sure that the building performs as it's designed, because you can lose a lot of heat and waste a lot of money by heat loss because it's not been done properly. because it doesn't then perform as it should.
Thank you. Jeremy Gibb asks, Jeremy Stacey, you mentioned an air mist system on the ground floor. Could you explain? That was a fire prevention system, was it?
It was a water mist system on the ground floor at number 9.
Yeah.
That's because the client wanted the ground floor to be completely open, which is a good idea because we had underfloor heating throughout the ground floor. And then there'll be a steady state temperature throughout all the rooms on the ground floor. And because the staircase came off that open area, the heat would rise up and not be wasted. Because if you put a fan at the top, it would blow the heat back down again. But because the staircase wasn't enclosed, there is a fire risk because you need to be able to have on a 3-story building, you need the staircase to go to a final exit. So when you escape from a bedroom upstairs, you can then leave the house without passing through any other room. So to get around that, a water mist system was installed, which is really a series of pipes, not many, and 6 or 7 sprinkler heads. And rather than having a sprinkler system, it's a mist. So it uses a lot less water than a sprinkler system. So it doesn't do so much damage if, the fire's only minor. But it was a way to get round having an open plan ground floor and the staircase being open to the ground floor area.
Thank you. And Brian asks, Brian, was that to either speaker in particular? Are these techniques all scalable? Is there enough hemp and wood wool available? And what is the source of LITAG? So that was to Natalie, I assume.
Okay, so in terms of scalability, I went to a talk at a place called Margent Farmer in September, and it was bought about 5 years ago, and they've got 2 demonstrator buildings on the site, and they grew their own hemp, and I'm not sure if they used it in, I think they probably used it on the building. I assume that that was its eventual use. But since that demonstrator building, there's a company called Hempspan who was highly influenced by what they were doing, and they're trying to kickstart the hemp growing industry so that hemp can be used and not have to be, you don't have to import that material. And they said that currently the natural materials market, natural building materials market, insulating materials that is, accounts for 1% of our insulation market. And I think my view is that it is scalable. It needs the demand, and it needs to be easier to get hold of. The companies who are providing it are mostly based outside of London, and whilst they're incredibly efficient and really amazing at supporting projects, because they're having to teach people who want to order their materials, they have to teach them how to use their materials, so they have really, really good technical departments, and they're also very quick at getting materials to you. There isn't that thing of the small builder being able to just pop down the road to a local Travis Perkins and pick up the materials as when they're needed. And that, I think, is possible for that to happen, but the demand and the understanding why the natural materials, one, work better, give you better indoor air quality and feel of buildings. If that understanding becomes more universal, there will be the demand, and then I believe the market will grow, and it will all become cheaper. And I would say also that wool, for example, is on a similar price point to the commercial, really commercial insulations. And wood wool isn't that far off. Not wood wool, wood fibre. Flexible wood fibre isn't that far off the price point of the commercial insulations.
Oh, that sounds hopeful. Yes. And what is the source of LITAG?
Oh, sorry, didn't. So LITAG, I'm not actually sure. It's something that was suggested by the concrete industry. I want to look into it a bit more. It's the reason it's interesting is because it's both. It can go into something. It can cope with, you know, a lot of weight. It can go in. It was able to go into the underpins, so it was able to cope with the weight of the building being on top of it. So it works structurally, but it's also insulating. But I need to look into that a bit more. But if Brian wants to get in touch, when I find out, I can let Brian know.
Thank you. Yes, and I was interested in our earlier meeting when you mentioned that you just use blocks rather than a whole concrete slab as the base for your new shed.
Oh,
I mean, what I'm getting at is, what I'm getting at is you can use less material, can't you, as well as a better type, more natural type?
Well, that all depends on what the structural engineer advises.
Sure. Yeah.
But you know, we're looking at a project at the moment where we're looking at doing pile foundations instead of you know, big solid ring foundations, which uses a lot more material.
Thank you. Are there any more questions, anyone? Helena said, thank you very much. I found the talks really interesting. I'd second that. So can I say thank you very much to Natalie and Jeremy for your time explaining your work. I found it all fascinating, and it's heartening to know that more and more is happening and more products are becoming available. So do a little clap. Thank you. Thank you very much, and please keep in touch because you know we need to keep people talking about these things. So that is the end of the Green Open Home Season 2022. Thank you for ending it with a bang. Remember, people are local installers list on the Muswell Hill Sustainability Group website. If you do use any contractors or renewables or natural building methods that you would recommend to your fellow members, we're not endorsing them as such, but let us know, because people are always looking for good people. And if you haven't joined MHSG or our mailing list, please do. Just drop a line to info@, thank you, Jeremy, info@mhsgroup.org. And I do hope we will meet again, Natalie and Jeremy. Please keep in touch and keep up the great work. Thank you very much for coming, everybody. Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Thank you.
Bye-bye. Thank you very much.
Good night. Good night.
Thank you, Mary. Oh.